So I'm Jujar Panesar, and as mentioned, I'm going to be talking to you about how there's no such thing as the perfect machine learning algorithm. First of all, I want to actually thank Dr. Andrew DeSantis, who's in the call here, who helped to prepare these slides. So thank you, Andrew, if you're listening. So feel free to contact us as well on hello@factorai.io, and we'll see how we can help. And the Twitter handles are there as well. So in terms of Factor AI, just a very brief introduction of who we are. So we provide artificial intelligence enabled real-time factory analytics for the production of formulated products. Now that's quite a mouthful. When you break it down into what that actually is in real life, we help manufacturers manufacture everyday formulated consumer products. So your Head and Shoulders, shampoos, your toothpastes, your hand washes, your creams, your Marmites, all the way up to chemicals like glycerin. And effectively, they're called formulated products, and a formulated product is basically where two or more ingredients are combined and processed in a specific way to obtain your well-defined target properties. In terms of how we do this, this is a typical industrial mixer that's used to manufacture those types of products, and you have your raw ingredients which enter your factory mixer. Your water, your oil, surfactants, emulsifiers, stabilizers, preservatives, perfumes, that kind of thing. All the chemicals that go into your everyday consumer products, and you have more than one or two streams, and they're processed in a specific way to give you your end product. The problem is this way of manufacturing has been it's been done for 40, 50, 60, 70 years. And what we're essentially doing is we're digitizing the process. So we're embedding sensors and outputting real-time data to give you, your agitator speeds and your viscosities and your densities and your temperatures and your acidities and salinities and that kind of thing, and really help manufacturers make compelling step change in the way they do things. So that's enough of Factor AI. I think we'll now move on to the machine learning side of things. I guess that's why you're all here. So in terms of machine learning, Arthur Samuels coined the term machine learning in 1959, and he defined it as the field of study that gives computers the ability to learn without being explicitly programmed. Now, it's regarded as a branch of computer science and artificial intelligence, and it's all about the data. Okay, all comes down to the data. So the actual machine learning basic workflow, irrespective of whichever algorithm you use, you're always following a basic workflow. So you have algorithms which operate by building models from training data, which is so-called training step. And effectively, you always have a raw data, the engineered data. So with the raw data, you implement all of your raw data and you do your exploratory data analysis. And effectively, in the engineered data, you do your model optimization. You make sure it's giving you the correct implementation. You cross-validate, and then finally you deploy the model. And you only deploy the model once you're comfortable with the model optimization. And then finally, of course, with your machine learning algorithms, you can make data-driven predictions. So the key definitions and concepts in machine learning, you effectively have two types of models. You have supervised models and unsupervised models. So supervised models are fairly simple. You have your input data. You want to know your output variable y, and effectively your supervised models are grouped into two. You have your regression and your classification. the unsupervised models, you take your input, you train your algorithm, and you can deploy them in a way that they're unsupervised, but they're more complex to implement, so to speak. Okay. So with regards to the key definitions and the concepts, effectively you have your input data, which is called your predictors or your features or your independent variables, whilst the output's called your response or your dependent variables. And believe it or not, when you're conducting machine learning or artificial intent, you're effectively solving this equation here. You have your output y, which is a function of some input x plus an error. And all you're doing is using algorithms to try and predict your function f. You're always going to have an error term when you use machine learning. Machine learning is it's not perfect. It will never give you 100% accuracy. But the aim of the game is to balance accuracy with implementation. And so the form f is generally unknown, and supervised machine learning algorithms, they always seek to find an estimate for f. And that's where your algorithms come in. And when you break it down further, you have, of course, a reducible error in machine learning. And this is the thing that we want to minimize as much as possible. And of course, you have your irreducible error. We can't do anything about that. So lastly, before I talk to you about different algorithms and some examples, I want to talk to you about training error and testing error. So when you train your algorithms to use your data to make compelling predictions, your training error is the error associated with the training data. And your test error is what's used to evaluate the model. It's unseen data, okay? And I guess the question is, when you train your algorithms, how do you estimate the error? How do you actually know what you're doing is right? And this is where the concept of cross-validation comes in. Now, a lot of these technical concepts, 20 minutes isn't going to do it justice. But it's just nice to know of it. And it's nice to then go off and learn about it yourself, or even attend our future workshops, the Lunch and Learn workshops. But effectively, with the cross-validation, you split your training data into test data and training data. You train your algorithms using your training data, and then you test it using the test data. And you're basically performing a self-diagnostic, a self-check. There are other validation methods, such as the leave one out CV or the K-fold CV, but I won't be talking about that. But you can look into that. It's a large field. Now here's where the key issue comes in with machine learning. It's all about making a trade-off. You know, do you go for the most perfect, most accurate machine learning algorithm, and do you spend years and years implementing it, or do you go for a slightly less accurate algorithm and take a fraction of the time implementing it? That's up to you as a practitioner to actually make that trade-off. And the way we do that is by making a sort of conscientious decision, really. So you can see here, there's a graph of model complexity, and there are many machine learning models and error. And you can see that, as obvious as it sounds, larger errors are associated with less complex models. And you can see two curves here. You can see a validation error, and you can see also a training error. Now, what you want to do is you want to, when you're using your data to train your algorithms, you want to get to a point where you have low validation error and as low training error as possible. And that's where you come into this little dip here. And that's effectively called, due to your bias variance trade-off. So your bias is the error introduced by approximating your complex real-life problems with simplified models. Okay, and the variance it's the measure of your variability of your function f. It's the algorithm using with the training data. Okay, and this is very important. This simple graph effectively tells you what sort of algorithm you want to go for. Okay. Now you could end up on the right-hand side where you have low training error but very high validation error, and that is a symptom of overfitting, right? So there is such a case of overtraining your algorithms. You don't want to overtrain, otherwise you'll have low training error but very high validation error, which is not good when you go to deploy these algorithms in the real world. So I'm going to be talking to you about two algorithms which are completely opposite of two extremes on the complexity spectrum. One is the linear regression, which I believe a lot of you on the call have probably used to some degree, perhaps without even realizing. And the other is the artificial neural network, which is the hot sort of algorithm spoken of today. Many other algorithms do exist, and many other machine learning algorithms do exist, but there's one thing you have to make sure that you understand: this so-called no free lunch theorem. And it's a concept that no single machine learning algorithm is better than all others on all problems. You, as the machine learning practitioner or the AI practitioner, it's up to you to determine which algorithm is best for your case. Okay, and we'll talk about the complexity of two algorithms here: linear regression and artificial neural networks. So with the linear regression, effectively you're fitting it's a linear relationship between your response and your predictors. In terms of what that means in real life, well, if you've ever fired up Excel and you have lots of data points and you want a line of best fit, that's effective. You know, that line of best fit is effectively regression. Okay, so you're applying the best fit depending on your data, and you might have some outliers in your data that will dictate the shape of your line of best fit. And that's effectively what you're doing here. You're doing a line of best fit, and you're using the line then to try and predict what's happening in the future beyond your data set. And you can see here that your line of best fit, your linear regression, it depends on these model coefficients, beta, and they're evaluated effectively by minimizing the residual sum of squares. So you're comparing your line of best fit to the actual data, and you want to reduce your RSS. Also, the most common metric to assess the accuracy of the model is this so-called mean squared error. And effectively, this slide summarizes quite well linear regression. I know you have three equations there, but effectively, as far as machine learning algorithms are concerned, it's fairly straightforward. Now you're going to see why I'm calling it fairly straightforward when you have a look at artificial neural networks. So with artificial neural networks, effectively, it's a collection of connected unit nodes called artificial neurons, inspired by the functioning of the biological brain. And effectively what you have are input layers. So your input layers accept your data, and then you have your output layer and a hidden layer. The actual hidden layer are the layers that do the work, and they're not layers that interact with the external world, okay? And effectively within artificial neural networks, all of these layers talk to each other in a complex way, and submodels actually tell you how these models talk to each other. And what you end up having, you can have deep neural networks where you have artificial neural networks with more than one hidden layer. And it's very possible to have many, many, many hidden layers. And this is where you need serious computing power, supercomputers, or computing on many hundreds of GPUs in order to actually solve these problems effectively. If you have large data analysis with 100,000 lines or even millions of lines of data, then you're going to need to solve on large computers. So with regards to the artificial neural network, effectively your perceptron represents a single neuron within your artificial neural network. So in terms of what that means, you have your inputs, X, which are weighted by associations. And of course, you have your bias, and you have this so-called signal, which is your activation function. Now, the reason why neural networks are complex and difficult to implement is because of this so-called hyperparameter. Now, hyperparameters cannot be evaluated from the training data. It's something that takes a long time to evaluate and train. So hyperparameter is one of the reasons why artificial neural networks and all these complex algorithms take so long to implement, and which is why you need powerful supercomputers just to implement. Now, with regards to the values of the weights to minimize C, you can use the so-called gradient descent. But there are talks within the scientific community about using other methods, such as the well-established Newton-Raphson method with line search to minimize your function C. So you can see now that you can see from here that you have a very simple, very straightforward linear regression, which is just line fitting, so to speak. And then you have artificial neural networks, which contain many complex hidden layers, whereby it can be very, very difficult and very complex to train due to this hyperparameter. Now, in terms of a real life practical example, what you could do is use existing medical records to predict the onset of diabetes in Native American Pima women. So this is a data set that you can publicly download on Kaggle. The link will be at the end of this presentation, and it contains the medical records of around 768 Pima women. They're Native Americans. And effectively, the data set contains 8 predictors. So you have your pregnancy, your glucose, your blood pressure, skin thickness, insulin, body mass index, diabetes, and age. And what you want to do is you want a response Y, and you want to know if they're tested, if you can use that data to predict if they're going to be tested positive to diabetes, that's a 1, or negative, a 0. And you can do this using linear regression or artificial neural networks. And the reason why you'd want to do this is because you want to identify risk factors. This is a real life example. You want to identify risk factors and take corrective actions. But especially pertinent today because a lot of companies and scientific institutions are using this kind of thinking to predict incidence rates in COVID-19 and to help then develop vaccines for COVID-19. So it's not something that's being plucked out of the air. It's actually being used in real life today, right now, to change the way, well, to help us go back to normality. This practical example here, I'll be covering it in another AI Tech North Lunch and Learn. So I'll be going through, and this is going to be in July, I'll be going through how you use those two algorithms, plus many more, to actually predict the outcome of diabetes using this data set. So if you want to use this data set and you want to learn how, join our Lunch and Learn session in July. So in summary, when you're performing machine learning, at the very least, perform linear regression. It's nice and easy, and you get an idea for what it tells you about your data. Increase complexity gradually. There's a plethora of machine learning algorithms out there. Don't jump straight to artificial neural networks, because it's quite difficult, and it takes quite a lot to understand it. Now, depending on your use case, you can have artificial neural networks accuracy using slightly cheaper models, for example, support vector machines. But don't go off thinking support vector machines is a cheap model, because it might be cheaper than artificial neural networks, but it's definitely more expensive than linear regression. And lastly, make sure you take an educated trade-off between model complexity and accuracy. You know, if you have something that's going to give you 99% accuracy, but it's going to take you 2 years to implement, or something that's going to be 95% accurate and only take a few months to implement, then you want to make that trade-off, 95% versus 99%. And that brings me back to this no free lunch theorem. You know, there's no single machine learning algorithm that is better than all the others on all problems. Okay, so I'm going to finally finish off with these useful resources here. Feel free to take a picture, and this is the website Kaggle, which I referred to earlier with the training set.